Okay, so, let me close the door. This is question 1, and it seems a little bizarre. I'm going to write the problem and then talk a little bit about it. But we have this problem. The t derivative of w is equal to the double x derivative of w, and we have w of 0 t s equals w of pi t s, and that's equal to 0, and w of x s s is equal to f of x s. Okay, now the setup to this problem, or this is the setup to doing Duhamel's principle, but I don't want to talk about that yet. Forget about Duhamel's principle. I know I just said it, but forget about it. What this represents is the following. So let's say we have the following problem. So this is the x-axis. This is the t-axis. And your boss comes to you and she says, okay, I know how to solve the heat equation when I have an initial data, when I know the initial temperature distribution. But for whatever reason, I need to know what is the solution to the diffusion equation or the heat equation going to be if I know, let's say, what happens if I don't know the initial temperature distribution, but I know what the temperature is at, say, time t equals s. Okay, and again, this is going from 0 to pi here. So what do I know? I know the boundary conditions over here. W will always be equal to 0, and W will always be equal to 0 over here. But she says, for whatever reason, I might not know the initial temperature distribution, but the data I might have might be for temperatures at time t is equal to s. So essentially then what we're doing is we're starting our diffusion equation not at time t equals 0, but at time t equals s, and it's going to go, in that time direction. We're starting from t equals s, and we're going up here. Okay, and so our data then is not f of x 0. What we know is f of x s. And so basically, we want to think about fixing a parameter, a time parameter s, and solving this equation. And then we can kind of use our results for whether or not we're starting from time there, or maybe we'll start from time here. We'll start at this time, and now f of x s is going to be the data there. Okay, and I'm going to basically separate this into 2 videos. The first video, I'm just going to remind you, or really kind of state explicitly something that we did in the practice problems. Okay, so if you go through and do separation of variables, so let's just think about the normal case where s is equal to 0, w of 0t equals w of pi t equals 0, w of x equals f of x. So that's like the thing that we've seen before, where we have an initial temperature distribution. Okay, what we do here is we do separation of variables. We say w of x t. Okay, so if you're taking notes, I'm going to be having big parentheses here, and I'll be putting an s there in a little bit, but not yet. In the next video, I'll put an s there. So we've got w of xt. We saw that this is equal to the sum, k equals 1 to infinity, bk of t sine kx. Now, when we first did separation of variables, how did we do this? Well, we separated variables, and we came up with the sine of kx functions, and then we came up with the h functions. But what I'm going to do is what we sort of did in the practice problems. Let's say we find out what the eigenfunctions are, and we know this is just going to be some function of t, and then now we're going to plug this into the ODE to figure out what they are. So I'm going to take this, plug it into the ODE. When I plug this into the ODE, I'm going to have this sum. On the left-hand side, I'll have the sum, k equals 1 to infinity. When I do term-by-term differentiation, only the bk, the differentiation in the t variable, only sees the bk, sine of kx is a constant. And so this is going to be bk prime of t times sine of kx. And on the right-hand side, similarly, when I take a derivative, the x derivative doesn't see the bk, so this is just bk of t sine kx. Okay, and I know that this solution, so I should have mentioned this before, but the point of the sine of kx functions is that this solution satisfies the boundary conditions. Okay, it doesn't matter what bk of t is. This function, no matter what bk of t is going to satisfy the boundary conditions. Okay, now we're trying now to get something that satisfies the PDE. And if I have these two things, these two functions are equal to each other, well, I have a sum of sine functions here and a sum of sine functions here. The only way these two can be equal to each other is if the corresponding coefficients are equal. So in other words, when I do the derivative here, there's a minus k squared. Sorry if you got confused about that and just thought about it for a few minutes and then just went on, and it's only now that you realize that I made the mistake. Sorry about that. bk of t, then this is going to be equal to bk of 0 times e to the minus k squared t. And so if I look at the function where if I replace bk of t up here, let me write it down here, I guess. W of xt is equal to the sum, whoops, I want to give myself some space here. W of kt, not yet, Rob, come on, dude. This is equal to the sum k equals 1 to infinity bk of 0 e to the minus k squared t sine kx. Okay, and now we know what to do. We're going to plug in t is equal to 0. If we plug in t is equal to 0, we've got w of x0. Well, that's equal to f of x. Again, we're imagining s is equal to 0. So that's equal to f of x and that's equal to the sum k equals 1. I'm going to move out of the way in just a second. bk of 0 e to the minus k squared t sine kx. Oh, sorry, if t is equal to 0, this is going to go away. That's going to be a 0. That's going to be a 1. And so we're just left with bk of 0 times sine of kx. In other words, this is the sine expansion of f, and so we know then that bk of 0 is equal to 2 over pi times the integral from 0 to pi f of y sine of ky. Sorry, I'm running into things. Okay, I'm actually not going to do this in two videos. I'm going to do this in one video. We have enough time. Okay, so now this is like what happens. What we've done over here is kind of the traditional case where we know the initial conditions. Okay, now let's look at this case. So what's going to change? Well, as this big space here suggests, I'm going to put an S there. Sorry, let me point out something else as well. This function satisfies the PDE and the boundary conditions. It doesn't matter what those are. This satisfies the PDE and the boundary conditions. And then when we choose the BK of zeros to be these guys right here, and and replace that with this formula. That's going to satisfy the boundary conditions and the initial conditions and the PDE. Okay, now to this problem, this is the boss that this is the problem that the boss wants you to solve. She says, okay, well, what if I don't know the initial temperature distribution, but I just know the temperature distribution at some other value? I don't know what value it'll be, so just kind of do this generically for me. Okay, now this is probably contrived. That's not the point. The point is I want you to think about what's going on here, and then once we solve this equation, we're going to use it to solve a non-homogeneous regular heat equation. Okay, so how are things going to change over here? Well, one of the reasons that we picked the sine of kx functions are that when you do the x derivative, you get minus k squared sine x, and it satisfies the boundary conditions. So we want to keep that part the same. So the thing that we're going to change now is bk is now going to be a function of t and s. See, if I'm doing separation of variables, I have to write it as a function of t times a function of x. And now s is involved too, so I'm going to make this also depend on s. So I need to have a product. I need to make sure it always satisfies the boundary conditions, so it makes sense that I'm going to leave sine of kx alone. Okay, so how does that change things down here? Instead of a prime, I'm going to write a partial t derivative here, and s over here. And so what does this give? This gives bk. Okay, now it's still an ODE in the t variable. S is constant, it's an ODE in the t variable. And so now what we're going to get on the right-hand side is bk of ts is equal to bk of s times e to the minus k squared t. Okay, so that's what we're going to have now. So this thing actually needs to depend on s. So this is the thing that's going to depend on s. And now if I look at this equation, okay, this still satisfies the PDE and the boundary conditions. Remember, we're thinking about s as being fixed. So this satisfies the PDE and the boundary conditions. Remember, this is not, like this right here, the bk of s isn't the thing that makes it satisfy the PDE, and it's not the thing that makes it satisfy the boundary conditions. This is the thing that makes it satisfy the initial conditions, or in this case, the t equals s conditions. Okay, well now how do I figure out what this is? Well, I'm going to come down here. I don't know, it's not that I know what w of x0 is, I know what w of x s is. Okay, so I know what w is when t is equal to s. So this is going to be f of xs, that's what this says here. And if I plug in s, I'm going to have an s here, and this will be e to the minus k squared s. Okay, now I need some space, so I'm going to erase this. All right, so now what's happening, this is saying that bk of s times, again, as far as x is concerned, s is a constant. So fixing s, just thinking about this is a function of x, and that's a function of x. It's saying that this thing right here is the coefficient for the sine function, for f. So in other words, this says bk of s e to the minus k squared s is equal to 2 over pi. Again, I'm going to use y as a dummy variable. This is f of y s sine ky dy. Okay, and if you define bk of s by this formula, so if I multiply, it'll give me the formula for bk of s explicitly. If bk of s satisfies this, then this function is also going to satisfy this condition here. The w of x s equals f of x s condition. Okay, so this is the solution. So this is the solution to the differential equation if we define bk of s this way. If you want, you can multiply things over there. And so now I'm going to erase this part right here. All right, so what's going to happen, I'm just going to replace bk of s with my formula over here. And what this is going to give me, so it's going to be kind of long, so I'm going to shift things over to the left. So what this is going to give me, this will be the sum, k equals 1 to infinity, Okay, bk of s, I'm going to write the integral part first, so that's 2 over pi. Here, I'll get down like this. 2 over pi times the integral from 0 to pi f of ys sine of ky dy, and now I'm going to have this exponential, but e to the k squared s times that exponential, so I can combine them into 1, and this is e to the minus k squared t minus s, and then sine kx. Okay, and so this function is a solution to this problem right here. Okay, that's it for this video. In the next video, we're going to use all of this. To solve a non-homogeneous diffusion equation. So stay tuned for that.